Okay, more questions on work energy. So our very first question is like this. There is a table, there is a pulley, and there is a block here. Its mass is m2 and this is a hanging block of mass m1 and coefficient of friction is mu, and let us say m1 is uh, going down, or you can say m1 is such that it can overcome friction on m2. It can overcome friction on m2 and pull it. System is released. Find speed of m1 or m2 because both will have same speed. By the time m1 goes down by distance L. So this is best done with work energy methods. Let's do it. If you draw the free body diagrams on m2, there is m2g, there is the normal force, there is tension, there is friction mu n, the kinetic friction, and on m1 there is m1g, there is t. So after this moves down a distance L, let us say it gets a speed v. This would have also moved to the right by distance L, it would have got a speed v. Now we will take both as one system. Why we can take both as one system? Because they have same speed. In work energy, if two objects have same speed, we can take it as one system. It doesn't work in Newton's laws because in Newton's laws we are dealing with acceleration, and acceleration is not same for both these blocks because their directions are at least different. So I can club both blocks and write work energy together. Work done by n plus work done by mu n plus work done by m2g plus work done by tension on m2 plus work done by tension on m1 plus work done by m1g is final kinetic energy of m1 plus m2 minus initial, which is 0. Now work done by tension on both blocks is together 0, because if this moves down by x, this moves to the right by x. Here work done by tension is plus tx, here work done by tension is minus tx, because both are in opposite direction, t and x. So that will be 0. So work done by tension together on both blocks, this term is 0. Work done by n will be 0 because it is always perpendicular to the displacement. Work done by m2g will be 0. Work done by mu n here is m2g. So mu m2g into minus L, because this block moved down by L, and m1 moved down by L, m1gl is half m1 plus m2 v square. How simple it is. So from here I can get v is 2 gl into m1 minus mu m2 by m1 plus m2 under root. If you do this with Newton's laws, it will take more time. You have to get acceleration, then use kinematics and so on. Let's see another problem. Suppose I have a hill like this. Let me do it on next page. Or I'll draw the diagram here. Okay, something like this. This height is 10 meters. This height is 2 meters. This is a smooth surface. And from here I am releasing a block of mass m. So this block, suppose, is coming like this. Sorry. It came here. And from here it's coming in a projectile path. So let me draw this properly. So it's coming in a projectile path and falling somewhere here. You have to find this distance x. That distance you have to find. Doing this problem with Newton's laws is very complex. So what we will do, we'll do with work energy. First, by the time block comes here, I'll find its speed. By the time it comes here, I'll find its speed. Then I can use projectile idea to find the range. So from A to B, I am applying work energy theorem. Work done by mg plus work done by n. These are the only two forces. Will be change in kinetic energy. Work done by mg, because mg is a conservative force. Whether you go in this path, or whether you go in this path, or whether you go in this path, or best whether you go in a straight downward path followed by rightward, work done by mg will be same always. If you go in the straight path, you are coming down by 8 meters, because total length is 10 and this is 2. So you are coming down by 8 meters. Work done in that process is mg into 8. Then you are moving horizontally, but mg is acting vertically. So work done in the horizontal path by mg will be 0. In the vertical path, the force mg is down and displacement 8 meter is also down. But in the horizontal path, the force mg is down, but displacement is to the right. So totally work done by mg is mg8. Whichever path you take, work done by mg is same, because it is a conservative force. Work done by n will be 0, will be half m into v square minus 0. So from here m gets cancelled. V is root 16 g. So I got the speed by the time the block comes to position B. Now from position B, this is 2 meters high. The velocity we got as root 16 g. Now we are planning to get the range. First we will do vertical kinematics. Vertically, initial velocity is 0. Acceleration in y direction is g. Displacement in y direction is 2. Because once it falls like this is the total displacement. This is vertical, this is horizontal. Vertical is 2 meters. So I am using vertical kinematics. And time is how much? So Sy is uyt plus half ayt square. Sy is uyt is 0, half ayt square, which implies t will be 4 by g under root. In that time, it is going horizontally. And what is the horizontal velocity? Root 60 g. There is no horizontal acceleration. So x displacement will be horizontal velocity into time, ut, plus half at square is 0, because ax is 0. So this will give me 8 meters. G gets cancelled, root 64 is 8. So the range of this is 8 meters. You can't do this problem that easily with Newton's laws, because the acceleration is continuously changing here in that curved path. So you have to use work energy. Then let us see some spring based questions. Suppose I have a block of mass m, and here is a spring constant k. Spring is relaxed and this is a smooth surface, no friction, and this block is coming with a velocity u. Find maximum compression in spring. So initially block was having speed u, but the moment it touches the spring starts exerting force on it. So so eventually what will happen? The block will touch the spring and compress it, and finally one day the block will stop because the spring retarded the block. So its kinetic energy here became 0. Initially it had kinetic energy half mu square. So let's apply work energy theorem. What are the forces on the block? Mg is a force, N is a force, there is no friction, and spring force comes from the moment it touches it. Is change in kinetic energy. Work done by mg is 0, because mg is down whereas displacement is to the right. Work done by n is also 0, because n is up and displacement is to the right. Work done by kx, spring is going away from natural length. When spring goes away from natural length, it will be minus half kx square, assuming spring got compressed by x. When spring is coming back to natural length, it is plus half kx square. We have seen this. That will be final kinetic energy 0 minus initial kinetic energy half mu square. So from here, the maximum compression in spring is m by ku square under root. Just 1 minute. हाँ भाई, हो गया क्या? कितना हुआ? 150. मैं आ रहा हूँ, थोड़ा टाइम लगेगा. आप रहते क्या? मैं 9 बजे तक आ जाऊंगा, क्लास में हूँ एक. नहीं नहीं, मैं आ जाता हूँ. 9 बजे तक आ जाऊंगा मैं. हाँ? नहीं नहीं बिल्कुल बिल्कुल यार, थैंक यू, हाँ मैं आ रहा हूँ. So so half gets cancelled and you get x as m by k u square under root. Yeah, this is, see, it's so simple. If you were to do it with Newton's laws, you have to integrate. How? At any moment when the spring is compressed by x, it exerts a force kx, whereas okay, let's write like this. So the acceleration is kx by m, and acceleration we write as v dv by dx, but you have to put a minus sign. A is v dv by dx, right? Actually, a is dv by dt, which you can write as dv by dx into dx by dt. But the problem here is dv is negative because the speed is reducing. So I am putting a minus sign. So if you write it as minus v dv by dx is kx by m, and then you integrate, minus v dv is kx by m dx, you integrate it. Initially compression in spring was 0, speed was u. Finally compression in spring is x, speed is 0. So if you do that, minus of 0 square minus u square by 2 is k by m x square by 2. This minus minus will become plus. So ultimately you get u square by 2 is k by m x square by 2, and from here you get x as m by k u square under root, which is the exact answer we got. But it is much easier, you see, in work energy, because we got work energy by already integrating Newton's laws. So you can directly apply it. If you use Newton's laws, you have to again integrate it. But we got work energy theorem by already integrating it from Newton's laws once and for all. So using that will be advantageous. So that is the idea here. Now, so most of the time you apply work energy theorem and you will get the answer. There is no big deal here. Now, I want to discuss about potential energy. This is a more complex discussion. Potential energy. So let me first outline all the conditions when you can define potential energy. Is it absolute or is it relative? What is absolute and what is relative, and all those conditions. See, rule number one, I am not even introducing you to the definition right now. I'm just giving you the outline, the boundary conditions. Potential energy cannot be defined for a single particle, or what I call as a free radical. Free radical. There is a single particle and there is nothing else except that particle. That means this particle is deep in outer space, for example, very far away from all galaxies and so on. Except this particle, nothing else is there. You cannot define potential energy for a single particle. Point number one. Potential energy definition requires at least two particles or more. Potential energy definition requires two or more particles. You can't define it for single particle. That means you are defining it for a system of two or more particles. System of two or more particles. So I'll just write here, we are defining potential energy for a system of two or more particles. You can't define potential energy for a single particle. You need minimum two particles, or 3, 4, 5, 6, whatever. Then third point, the forces between the particles of system must be conservative. There must be forces first between the particles of system, and the forces between particles of system must be conservative. So what am I saying here? I am talking about internal forces now. Internal forces means the forces between the particles inside the system. System consists of two or more particles. So forces within the system must be conservative forces. Otherwise, you can't define potential energy. So potential energy requires minimum two particles or more. It cannot be defined for a single particle. Okay. And The forces between particles of system must be conservative. Even after this, potential energy requires a reference. Potential energy definition requires a reference. Requires a reference. We'll see what it means. So actually potential energy is not absolute. Change in potential energy is absolute. It will be fixed for all observers who are calculating it. But potential energy may be different for different fellows. So potential energy may be different for different persons because their references are different, because they have taken different reference points, because they have taken different reference points. Okay. However, change in potential energy is same for all. That is absolute. What is all this? It looks very confusing. So let me right away give an example to make you understand. Suppose I have a block of mass m kept on a floor. Now we are trying to define what is called gravitational potential energy here. Okay, maybe you have some idea already from lower classes, but we are going to make it more rigorous this time. However, to start with, I am borrowing some ideas from lower classes. So I have this block of mass m. Many people say when you take the block to certain height, it has potential energy. They say that the block has potential energy, but technically it is not correct because just a single object cannot have potential energy, right? There must be at least two objects or more than two. So what is the other object here? See, for example, if I take it to a height h, people say potential energy is mgh. They write like this. The question now is, what is the other object? You are writing g, and g comes only when there is earth. So implicitly they are saying that there is another object called earth. So there are now two objects. Okay, one is the block, one is the earth. There must be two or more to define potential energy. So here in this case there is the block and the earth, and the force between block and earth, which is the gravitational force, is conservative. Hence we are able to define potential energy. So you look at the conditions now. Potential energy cannot be defined for a single particle. Even though you are saying it's potential energy of the block, there is earth. If there was no earth, there is no question of defining potential energy. So here there are two particles, the block and the earth, for which we are defining potential energy. Second, the forces between these particles must be conservative. So are they conservative? Let's check it. The gravitational force between block and earth is definitely conservative. Gravitational force is conservative force. Now, so under this condition, we can define potential energy. A person now standing here will say the block has zero potential energy. So at this level, potential energy is zero. And suddenly when the block went to height h, he will say potential energy is mgh. Now suppose there is another person who is standing here, person 2. He is much below person 1 and he is at a depth h1 below person 1. So person 1 is on the ground floor and person 2 is in the basement parking, let us say. For person 2, the block is not at his ground level. This person 2's ground level is the basement. The basement. But the block is not at his ground level. It is at a height h1. So for this fellow, if I write in blue color, for this fellow, the potential energy here is mgh1, not mgh, not 0. And potential energy here is mgh plus h1. So now you see person 1 and person 2 are talking on a mobile phone and they are quarreling. Person 1 says, hey, when the block was here, the potential energy is 0. But person 2 says, no, 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 its potential energy is mgh1. They are arguing. Both are correct because both references are different. For person 1, ground floor is the reference. For person 2, basement is the reference. So according to person 1, the block is at his same level initially, so its potential energy was 0. That is when the block was here. But for person 2, block is already raised by a distance h1. So he says potential energy is mgh1. So both are quarreling now. On the other hand, when the block goes to height h, person 1 is saying the potential energy is mgh, whereas person 2 is saying potential energy is mgh plus h1. Again, there is a quarrel. But note one thing, the increase in potential energy for both is same. This fellow says potential energy is increased by mgh, or change in potential energy is mgh. This fellow also says change in potential energy is mgh. That is what I wrote here. Okay, potential energy may be different for different persons, but change in potential energy is same for all. What is more important for us is change in potential energy, not individual potential energy values. We always in our mathematics include change in potential energy. So with this background, now let me define. I will define first potential energy by taking a reference. Then I'll give a more general definition of change in potential energy, which doesn't require any reference. So let's define potential energy of a system of particles. Okay, so potential energy of a system of particles is work done by external agent, some external fellow, to assemble or bring together all particles from infinity to the required distance. What is it that I am saying? Suppose I saw three particles here and I want the potential energy of the system. What you should do is you must find the work, and I must use the word slowly here. You must find the work done by external agent to bring the particles to this configuration. So originally you will assume that all the particles were at infinity. I'll call these particles as 1, 2, 3. All these three particles were at infinity. So first you brought particle 1 from infinity and kept it here. For that you don't need to do any work. Then you are bringing particle 2. When you are bringing particle 2, the particle 1 will exert some force. So you need to do some work to bring it slowly. You are always bringing it slowly. Okay. Then you bring particle 3 also very slowly. And in this process, whatever work you have done, that becomes potential energy of the system. But here you are taking an assumption that potential energy at infinity is zero. That is the assumption. So potential energy is work done by external agent to assemble the particles by bringing all the particles slowly from infinity to the given position. That will be the potential energy of the system. Okay, for example, or I'll define change in potential energy, which is more better. Change in potential energy is work done by external agent. So I'll write here work done by external agent. This is much better to change configuration of system. Configuration means arrangement of particles and so on. Configuration of system slowly. That is change in potential energy. So you are defining it in terms of work done by external agent to change the configuration of the system slowly. Let's directly take an example and understand it. Suppose I have a block of mass m. Okay, and suppose the block is now being taken to a height h. I want change in potential energy. We know if you take it 0, this is mgh, change is mgh. Or if you take it mgh1, this is mgh plus h1, change is still mgh only. Change in potential energy will always be same. Individual potential energies may change. I am defining change in potential energy only. So how am I defining it? Work done by external agent to take this, to change the configuration. What is the configuration here? Earth and block were initially touching. Now the block is being separated from earth. So you are changing the arrangement of earth and block. They were originally touching. Now you are separating them. That means you are changing the arrangement or the configuration of the earth block system. So whatever work is done by external agent to change the configuration slowly. How will he change the configuration slowly? See, originally earth was exerting a force mg, and of course n was also there. Now suppose if he applies 10 mg, then this block will shoot up. It is not changing slowly. So how do you change slowly? You will apply a force slightly more than mg in the beginning, slightly more than mg. And once the block starts moving, you keep the force back to mg only. So once you bring the force back to mg, net force is 0, and whatever small velocity it gained, 1 millimeter per million years, it continues with that and reaches this position in million years. So effectively, what force you applied? You applied mg only. Of course, you can counter me and say, no sir, initially I applied slightly more than mg, but that was only infinitesimally slightly more than mg to get the block started moving. Once the block starts moving, you applied mg only. So net force is 0. Block continues to move with that small velocity. So effectively, by the time it reaches height h, work done by you will be mgh, because you applied mg and the block went up by h, and it went slowly. So whatever work done by you in this case is mgh, and work done by you slowly is change in potential energy. So change in potential energy is mgh. Work done by you slowly. So change in potential energy is mgh. So how do you calculate change in potential energy? First, bring an external agent. It may be you or me or somebody. And then we have to change the arrangement or configuration of particles slowly. In this process, whatever work we do will be changing potential energy. If you do the work fast, you are changing potential and also kinetic. So work done by you will be change in potential plus kinetic. For example, look here. Suppose this block M is there. I want to take it to height h. One way is Earth is pulling it with mg. You also apply mg. But if you apply mg, how will the block move? So initially you apply slightly more than mg. Once the block starts moving, once the block gains some velocity, then apply mg only. Net force is 0, but it has velocity, some very small velocity. So it will come there, and work done by you will be mgh. That will be change in potential energy. But suppose instead of applying mg, I applied 10 mg, then block won't go slowly, right? What is the acceleration? Net force by mass. So 9g is the acceleration up in that case. By the time it reaches height h, it would have gained some velocity. How to get that? V square minus u square is 2as. 2a is 9g into s is h. So what is the kinetic energy it gained? Half mv square. That is half m into, we already calculated v square na? So it is 18 gh. So total it will be 9 mgh. So you see, kinetic energy is 9 mgh. Potential energy is still mgh only. So whatever work the person did, 10 mgh. Why he did 10 mgh? He applied 10 mg and it went up by h. Whatever work he did, it increased the potential plus kinetic. Kinetic became 9 mgh. Potential is still mgh only. Okay. So better is you do the work slowly. Whatever work you do is only change in potential energy. If you do the work fast, the work you do will be change in potential plus change in kinetic also. But we can do a clever thing. Even though your force which you are applying could be mg or 10 mg or 9 mg or whatever, gravity will always apply mg only. That's the beauty. So instead of saying work done by you, if I say negative of work done by gravity, it will be safe. For example, you are applying mg, gravity is applying mg. The block went slowly to height h. Okay. Potential energy is mgh. You can say that is work done by you, which is mgh. Or you can also say potential energy is negative of work done by gravity, negative of minus mgh, because gravity is acting down and block went up. So gravity did negative work. Negative of you're able to hear Hamna?
Yes, sir.
Okay, okay. There is a power cut here. So uh, work done by gravity is minus mgh. Negative of that will still be mgh. That is change in potential energy. Now here it doesn't matter even if you take it fast. Suppose you applied 10 mg, no problem. 10 mg. Gravity is still mg only. So work done by gravity is minus mgh. Negative of that is still change in potential energy. So you can avoid the word slowly by defining it like this. Change in potential energy is negative of work done by gravity means conservative force, which is acting between the particles. Negative of work done by conservative force in changing configuration of system. Now slowly what is not needed, because no matter what is your force, gravity is still the same. It never changes. Okay, your force may be more, then you are doing work to increase potential plus kinetic, or your force may be exactly equal to conservative force, then you are doing work only to change potential energy. So your force may change, but gravitational force is always the same. So you see this example, when you applied mg and slowly took the block to height h, you did mgh work, but you did it slowly, so it is changing potential energy. Whereas if you applied 10 mg, whereas if you applied 10 mg, the block would shoot up. So the work you did increased both potential and kinetic. So if you do slowly, you are increasing potential. If you do fast, you are increasing potential plus kinetic. But no matter what is your force, gravity is always mg. Work done by gravity is always minus mgh. Negative of that will always be plus mgh, which is increase in potential. So there are two ways to define change in potential energy. You can define change in potential energy as work done by external agent, but in that case you have to use the word slowly, because if he does fast, he's also increasing kinetic. The other way is you define change in potential energy as negative of work done by the conservative force, maybe gravity, spring, whatever. In that case, slowly is not required. Hell with the external agent, he may do work fast to slow, but conservative force always does same work. Okay, so these are the two definitions of change in potential energy. So once again, change in potential energy can be defined as work done by external agent to change configuration of the system slowly. If you say work done by external agent, you have to use the word slowly. Other way of saying change in potential energy is negative of work done by conservative force in changing configuration of system. Slowly not required now, because your force may change, but conservative force is always the same. So slowly is not required. So this example is a very important example. The block being taken to height h, which I said. Okay, it's a very important example. So these are the two definitions of change in potential energy. So I can write change in potential energy. I'm converting this into mathematical statement, is negative of work done by conservative force means integral f dot ds, where this is the conservative force in changing configuration from initial to final. Okay, generally we use the symbol u for potential energy. So instead of writing delta p dot e, I will say delta u. I can write delta p dot e or delta u. U is the symbol we use for potential energy in physics. So change in potential energy is negative of work done by conservative force in changing configuration from initial to final, slowly not required. Whereas if you define it in terms of external agent, work done by external agent in changing configuration from initial to final, slowly required. Okay, both definitions give same answer, but first one is more convenient because you are not placing any restriction called slow or fast. But in second, when you find work done by external agent, the restriction is important. Okay, now what is the reverse of this? The reverse is force is given by minus del u. Yesterday we saw del operator, na? I dou by dou x plus j dou by dou y. For example, if potential energy is given as x square yz, what is the force, conservative force, which resulted in this potential energy? Minus I dou by dou x of x square yz minus j dou by dou y of x square yz minus k dou by dou y of x square yz. What am I doing? I am doing minus del u. Okay, what is del? Del is I dou by dou x plus j dou by dou y plus k dou by dou z. This is an operator. You can operate it on a scalar directly. So potential energy is a scalar, 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 scalar. But del u is not force. Minus del u is force. So I would put a minus sign here. Minus del u. Okay. So that's the reverse. So if you know potential energy, you can get force by doing del operator. If you know force, you can get change in potential energy by using integral. Okay, both these are very important. So in this case, what will be the answer? Let me check what is the answer here. Minus I dou by dou x of x square yz. Partial derivative, only x is the variable, y and z are constants. So yz into 2x minus j dou by dou y of only y is the variable, x square z dou by dou y of y is 1. Okay, minus k x square y. So minus yz into 2x I minus x square zj minus k x square y is the force. Only conservative forces can give potential energy, because work done should be path independent. It should be configuration, position dependent and path independent. And potential energy is defined only when there is a force which is position dependent and path independent. Okay, because you bring it to that position, you should have that potential energy, no matter in what path you bring it. So that is the connection actually between conservative force and potential energy. Okay, so once again, let me uh, tell you, let me go back and revise this bit, because this is the critical part of this chapter. So potential energy cannot be defined if there is only one particle. There must be two particles, because only then there will be forces between them and you can define potential energy. So minimum you need two particles. The other point is the forces between particles of system must be conservative. Otherwise you can't define potential energy. Why? Because if the forces are non-conservative, for every path you do different work, even though you bring it to the same final situation. Then for every path, one fellow will say potential energy is 10, other will say 20, in spite of having same reference. So it won't work. And that energy cannot be recovered also if it is non-conservative force, like friction or something. So the forces must be conservative. This is the condition. Then potential energy absolute value may be different for different fellows, but change in potential energy is same for all people. That's why we are defining change in potential energy. How do we define it? It is defined as work done by external fellow to change the arrangement from one position to another slowly. Work done by external agent to change the configuration or position or arrangement of the system slowly. Okay. If you are saying external agent, slowly is a must. The other way of saying it is negative of work done by internal conservative force. When you say that, slowly is not required. The reason for that is this example of the block. Okay, you took the block from here to here by height h. The change in potential energy will be mgh. How did you get mgh? Method 1. If the person is doing work slowly, means block should not accelerate, means he should apply same force as mg only, the gravity. Then the question might come for you, sir, how is the block moving? Okay, initially I applied a slightly more force so that block starts moving. Once it started moving, I applied mg only. So net force is 0 now. Upward my mg and downward gravity mg. If net force is 0, block will slowly continue with that speed and reach height h. Slowly means almost with negligible kinetic energy. So whatever work I did in this process, I am applying upward mg and displacement is h. mgh will be change in potential energy. So work done by external agent slowly. If you don't do slowly, what you are doing? You are increasing potential, but you are also increasing kinetic speed. Also you increased. So in general, work done by external agent goes as change in potential plus kinetic. But if you do it slowly, it will go as only change in potential. So when external agent does work, slowly is must. But you see one thing, whether you apply mg or 10 mg, gravity is mg only. That's the beauty of gravity. So what is work done by gravity? Minus mgh. But potential energy was mgh. So you again put a minus sign. So negative of work done by gravity is change in potential energy. Or you can say negative of work done by internal conservative force is change in potential energy. In that case, slowly is not required. Why? Because the gravity is always mg only. It is not changing. Your force may change 10 mg, 8 mg, 5 mg, but gravity is same. So whether you take fast or slow, gravity is mg only. Work done by gravity is minus mgh. Change in potential energy will be mgh. Okay. So I converted this into a mathematical statement. Change in potential energy is negative of work done by conservative forces, means integral F dot dr. What is F here? The conservative forces in changing configuration of the system from initial to final. This is the mathematical definition. So from a vector force, by doing some dot product and minus sign, we got a scalar called potential energy. The reverse operator, given potential energy function, how do you get force? By doing del operator and putting a minus sign, you get force. So both the conversions are very important. You should know both the conversions. Given conservative force, you should know how to calculate change in potential energy. Given potential energy function, you should know how to calculate the conservative force. Both are very important. Okay, so I hope till here it is clear. Now, first, let us look at the spring force. We already saw spring when it was in natural length, and from there you expanded it to an expanded length. In this case, the work done by spring force was minus half kx square. We got it by integration. So, negative of work done by spring force, which is a conservative force, will be change in potential energy. So, change in potential will be half kx square. Generally, in spring problems, when spring is natural length, we take potential energy as 0. And in the expanded state, it is some u. So, change in potential energy will be half kx square. That means in the expanded state, spring potential energy will be half kx square. Because in natural length, you took it 0. Similarly, when you compress the block, work done by spring is again minus half kx square. Negative of work done by spring force is plus half kx square. That should be change in potential energy, u final minus u initial. But u initial you took 0 at natural length. So even in compressed state, potential energy is half kx square. So whether you expand or compress the spring, potential energy becomes half kx square. You release the spring, this potential is given back to you. Suppose a compressed spring is released, it will push the block and give kinetic energy to it. Okay, so potential energy of spring in expanded or compressed state is half kx square, provided potential energy in natural length is taken to be 0. Okay, this is a very important concept. Now all the problems that we have done with work energy theorem can be done with a new theorem which we are going to derive now. So you see, I'm going to derive a new theorem. What is that? We know from work energy theorem, work done by all forces, no exception, is change in kinetic energy. You can apply it to particle or group of particles also. Work done by all forces, external, internal, conservative, non-conservative, no restriction. All forces should be change in kinetic energy. Now, in these all forces, we can bifurcate them as some are conservative, some are non-conservative. Okay, we can bifurcate like this. Okay, in conservative also, depending on your system, there can be external forces, there can be. So what I'll do first, I will not bifurcate like this, rather I'll bifurcate it as external and internal first. Work done by external forces plus work done by internal forces. So all forces means external to the system also, internal to the system also. It depends on what you take as system. You might take 2 blocks as one system, 5 blocks as one system. That is up to you how you want to take. But it will give change in kinetic energy of system. Now in the internal also, external I don't do anything. Internal I can again split into internal conservative force and internal non-conservative force. Internal can be again bifurcated like this. External can be anything, I don't care. We take this internal conservative force to the other side, then what it will become? Work done by external plus work done by internal non-conservative will become change in kinetic energy plus negative of work done by internal conservative force. We just now saw negative of work done by internal conservative force. This one is change in potential energy. So we can write this fellow as change in potential energy. So we get a new theorem, work done by external forces. External, there is no restrict, all external, it's whether conservative, non-conservative, I don't care. All external plus work done by internal non-conservative will give change in potential plus change in kinetic. This is a very powerful theorem. Okay. There is a special case in this theorem which we will discuss now. Suppose it so happens that external forces don't do work, or they may not be there. Even if they are there, they don't do work. Similarly, internal non-conservative forces don't do work. Then what happens? Change in kinetic. So K final minus K initial. This change in potential, U final minus U initial will be 0. From here you can check K final plus U final is K initial plus U initial. Kinetic plus potential is called mechanical energy. So mechanical energy final is mechanical energy initial. This is called law of conservation of mechanical energy. Law of conservation of mechanical energy. Okay. So when is mechanical energy conserved? Look, when work done by external forces is 0 and work done by internal non-conservative forces is 0, then change in potential plus kinetic is 0, then mechanical energy will be conserved. So law of conservation of mechanical energy states that when work done by forces external to the system is 0 and work done by the internal non-conservative forces is 0, then mechanical energy is constant. What happened to internal conservative force? They went to the other side and it is taken care by the potential energy term. See, internal conservative force was taken care by writing it as change in negative of work done by internal conservative forces, change in potential energy. Okay. Now, how can we use this theorem to do problems? Let us see what problems we did. If you remember, one problem we did where the inclined was half smooth. It was the block was released from height h. The inclined was half smooth. This part was smooth and half rough. This part was rough, and the block exactly came to rest at the bottom of the incline. Inclination is theta. We asked coefficient of friction. We did it with work energy theorem. Now I will do with this special theorem. What is it? First you will choose your system. What is your system? You can take only block as system. If you take only block as system, all forces become external. It's as good as work energy theorem. But I'll do in a slightly different way. I'll take whole universe as my system. Whole universe is my system. Then all forces become internal. So let me write the statement. Work done by external forces plus work done by internal non-conservative force is change in potential plus change in kinetic, right? If you take whole universe as system, what is external to universe? Nothing. So this is 0. What are the internal non-conservative forces acting on the block? Gravity is acting, but that is conservative. Friction. So work done by friction, non-conservative, is change in potential. Now, all conservative forces which are internal will give potential. So, initial potential energy is mgh. Block is at height h. Finally, it came down 0. So, change in potential is final minus initial. Okay. There is only gravitational potential energy here. No spring, nothing else. Change in kinetic. We saw that it started from rest. It came to rest. So, work done by friction is minus mgh. Friction does work only in the rough part. Minus mu mg cos theta into h by 2 sin theta. That is work done by friction. That is minus mgh. So mu v is 2 tan theta. That's exactly what we got. That's exactly what we got. If you see today's problem, which we have done, I did a problem like this now. So let me try to draw it properly. I did a problem like this, where this height was 10 meters, this height is 2 meters, and I released a block from here and it came down in this path, and from there it fell as a projectile. I asked it this range, right? Till here we applied work energy theorem from A to B. Now again I'll take whole universe as my system. Then there is nothing external, all are internal. What are the internal forces? Mg is there, normal is there. Normal doesn't do work. So only Mg is there. That means there is only internal conservative force. Non-conservative force normal did not do work. External nothing is there because whole universe is my system. So external forces don't do work. There is no external force. Internal non-conservative normal doesn't do work. So mechanical energy is conserved. That means potential plus kinetic. K plus U is constant. So I can write K plus U at point A equal to K plus U at point B. Potential at point A, mg10, kinetic is 0. Potential at point B, mg2. I am taking ground as reference for potential. Okay. You could have taken point B as reference and done it. That's also okay. Plus kinetic at B is half mv square. So mg10 minus mg2 is 8 mg is half mv square. So we got V as root 16g like previous method, and from there you can use projectile and solve the problem. So here we are using mechanical energy conservation. Why we are using mechanical energy? We took whole universe as our system, so there is no external force. Everything is within the universe. Second, if there are any internal non-conservative forces doing work, we must include that. But there is normal, but it doesn't do work. So work done by internal non-conservative is also zero. So go back. If work done by external is zero and internal non-conservative is zero, it goes into mechanical energy conservation. So mechanical energy is conserved. Potential plus kinetic initial and final should be same. Initially block was at 10 meters height. Potential is mg10. Kinetic is 0 because it is starting from rest. When it came to B, potential is mg into 2. Kinetic is half mv square. So I equated these and I got V is root 16g. It's a very powerful idea what we are getting here. So we can do like this. So this work energy theorem only I modified and made into this theorem. So let me write both of these. One is work energy theorem. You can use that to solve problems. It's very simple. Work done by all forces, no exception, internal, external, conservative, non-conservative, nothing, all is change in kinetic energy. This is work energy theory. Or you can use work done by external force. What is external? First you must choose your system. What is your system? Suppose, there was a problem where there is a spring, there is a block, and there is earth. Suppose you say spring and block are my system. Then spring force will be internal conservative, but gravity will be external. If you take spring, block and earth as your system, then spring is also internal, gravity is also internal. So you should know what is your system first. You should define your system. Then work done by forces external to the system plus work done by forces internal but non-conservative to the system will be change in potential plus change in kinetic. Potential, how you are defining? It is only for internal conservative forces you are defining potential. If there is external conservative force, it is coming as external force here. Work done by external force. If both these are zero, it becomes mechanical energy conservation. So these are the theorems which we will use to solve many more problems in our next class. Our next class will contain only problems now. Theory part of work energy is over. I am left with power. Okay, I will define it here. What is power? How fast something does work, or rate at which work is done is power. But we know dW is F dot ds. So F dot V is the power of a force. This is what we call as instantaneous power. So power is rate at which work is done. Suppose I also do work, you also do work. Same work we are doing, but you do it in 1 hour, I do it in 10 hours. You are more powerful because you did the same work in less time. Same work, but time is less, power is more. Okay. So the exact definition of power is rate at which work is done, but dW is F dot ds. So you can write it as F dot ds by dt or F dot V. Average power, how to define it? Average power, you have to take instantaneous power, integrate it with respect to time by time interval. This is how we calculated average for any quantity in kinematics. Okay. Now, what is average? What is P in dt? You look from here. P dt is dW. So it will become integral dW or W by t. This is average power. I told this also. If you just divide something by time, that is average. If you take derivative, it is instantaneous. For calculus lectures, I said rate of change of height of a baby is dH by dt. Whereas if you do change in height by change in time, it is average rate of change. Same thing here. Exact power is dW by dt. Average power is W by t. Same idea. Exact power dW by dt, you can write it as F dot V also. Okay. So we will in the next class, we will work on problems on using both these theorems. Very complicated problems we'll do from here, not simple ones. I'll make you do very complex problems, and we'll also do problems related to power and things like that. So that is what we have here. Now, theory point of view, I have done everything here. Nothing else is left from theory point of view. Only problems are remaining, which we will do in next class. So any doubts in whatever I said today? Is it fine?
No, sir, no doubts.
Okay, excellent. So we are doing excellent. We are at a good pace. So I'll send you these files. I'll just close it and send you these files.